Let's consider Lenz's law from a slightly different perspective. We just saw it in the last video where we had a moving bar in a magnetic field. Now, let's have, instead of a bar, let's imagine a solid rectangle of copper wire that's going to remain stationary. And instead of having that moving, we're going to have the magnetic field moving in relation to it. Just so we're all on the same page, I marked one side of this with some black dots. We're going to concentrate on the left side of that loop of copper wire for our discussion, but we could be talking about any side of it. But again, just want us to all be talking about the same thing. So I'm going to take an imaginary bar magnet, and I'm going to put it so that the south pole of that bar magnet is above our loop of wire. And when I do, I hope you can see that we have a bunch of magnetic field lines that are coming out of the board. Now, if I pull that bar magnet away, look what happens to those field lines. They move out of the inside of the loop. Let's watch that again. Field lines are in the loop, and now they move out of the inside of the loop. Oops. As I pull the bar magnet away. Now, if the field lines were moving this way to the left in our picture, across the left side of the rectangle of copper wire, do you think that copper wire would know or even care that the field lines were moving relative to it, or if it were moving relative to the field lines? Remember, it's just a bar of copper wire. It doesn't know what's happening around it, but it does have the same experience if it's moving in a magnetic field or if a magnetic field is moving near it. So, if you were that leftmost side of the rectangle of copper wire, while the field lines would be moving right to left to you, it would be the same effect on you as if you were moving left to right relative to those field lines. So let's take a moment and think about what that would mean as far as the current inside the wire. So pause on that for a second. And we're back from our pause. As the field lines moved right to left, it's the same thing as the copper bar moving left to right. So imagine a copper bar moving left to right in this configuration. Our field lines are coming up out of the board. If the bar is moving left to right, then there's a force on the positively charged particles in our wire that is towards the bottom of our picture, meaning we get a current flowing this way. As that current flows in that direction, can you tell me what is the direction of the field created by that current inside the loop? Take a moment and think about that. And you're back. Using the second right-hand rule, imagine grabbing this wire from underneath with my thumb pointed to the right in my picture. There we go, sorry. And we see that inside the wire, the field lines are coming out of the board. Whoa, magic, there we go. The field lines have magically popped into view, and we need one more task now. Let's reconcile for ourselves how does Lenz's law, which tells us that the current opposes the change in flux, how does Lenz's law reconcile itself with everything that we just saw? Take a moment and think about that. And we're back from our pause. And if you thought that while the field lines were moving out of our loop, the flux was decreasing, of course you were right, but the current that's induced by that decreasing flux will try to oppose that decreasing flux by creating a field that's coming out of the board inside that loop, which is exactly what we got in our analysis using motional EMF, and we get the same exact result if we think about it in terms of Lenz's law and Faraday's law of induction. So, a pretty complicated little story there to tell, but I hope between these two videos it kind of made some sense to you. And thank you again for watching. Take care.